This lesson is your introduction to differential equations, and I gotta tell you, this is one of my favorite topics in this entire course. Differential equations are really fun and exciting, and they can describe cool stuff, as I will soon tell you. But first, I just want to explain what a differential equation is, and a differential equation is an equation for an unknown function, and it involves derivatives of that function. And so it's helpful to contrast this with what you're used to from algebra. In an algebraic equation, the unknown is a number, right? So 2x minus 5 equals x plus 1. The thing you're trying to figure out is what is x, and x is just, in this case, a single number, and that happens to be 6. In a differential equation, the unknown thing is a function. So we might see the unknown thing itself appearing, and we also see derivatives of that thing. So when I look at this equation, I see a derivative, dx dt, that already tells me this is going to be a differential equation. Since x is in the numerator, I know that x is the dependent variable, t is in the denominator of the derivative, so t is the independent variable. All right, so when I look at this, I see that we have an equation that says the independent variable t times the derivative of some unknown function x equals 1 plus 4 times that unknown function itself squared. And that's an equation for an unknown function x of t. That's a differential equation. It so happens that the solution to this is 1/2 tangent of this expression here, where c can be any constant. Okay, you don't have to worry about that. That's a bit beyond this class, but I just wanted to give you an example of a differential equation and its solution here. So who cares? Well, differential equations are, among other things, models of change, and that's the way we will think about them in this course. We'll think about differential equations as describing things that change, and usually change in time. And it's super exciting because they can describe so many interesting things. The macroeconomy, the immune system, the spread of epidemic disease, stuff that goes on in our ocean and atmosphere, movement of astrophysical bodies, social behavior, crime, and so many other things. Almost anything you can think of might have differential equations related to it. And we don't use differential equations for these things just because we can. The main point is that for many of these systems, it's easier to know how something changes rather than the thing itself, right? So if we ask the question, you know, where is all the water vapor in the atmosphere? That's a really hard question to answer. However, from physics, we know the rules for how water vapor moves around in the atmosphere. And so we can very simply write down those equations. They happen to be differential equations. And then the idea is that if you can solve those differential equations, then you'll get the answer to your original question. So again, that's the main idea, is that sometimes it's easier to know how something changes rather than the thing itself. So you start from knowledge of how the thing changes, that's a differential equation, then you solve it. Our focus in this course is going to be ordinary differential equations, which I'll call ODEs, and this means differential equations where the unknown function has a single independent variable, okay? And as I kind of already alluded, for most of our applications, that independent variable is time. In this course, we'll study either single differential equations or sometimes system of differential equations. Just like you could have systems of algebraic equations, you can have systems of differential equations. So you might be interested in describing, for example, in the spread of an epidemic, how the number of people susceptible to a disease and the number of people infected with the disease, how those things change in time. So that's two independent variables, two dependent variables and one independent variable of time. So that's an example of a system of differential equations. You'll see those in a bit. And usually our equations will be in this form, you know, dx dt equals something. Differential equations don't have to be in that form, they just have to be equations for an unknown function involving its derivatives. But for this class, usually the formula will be dx dt equals blank. So that's just simply writing down a very simple rule for how x changes in time. And often this is paired with what's known as an initial condition, and I'll explain a little bit more about that once we get into some examples. So let's talk about what it means to be the solution of a differential equation. Well, a given function is the solution to a differential equation simply if plugging it in results in a true statement. And again, it's helpful to fall back on algebra here, algebraic equations. So we could take as an example 3x minus 2 equals x squared minus 6, and I could ask you the question, is x equals 4 a solution? And if I asked you that question, you would all do the same thing. You would plug into the left side, and you'd plug into the right-hand side, and you'd see if the left-hand side equaled the right-hand side, and if it did, then you'd say, yes, it's a solution. So let's go ahead and do that. The left-hand side, we get 3 times 4 minus 2, that's 10. On the right-hand side, we get 4 squared minus 6, that's 16 minus 6, which is 10. And then you say, aha, the left-hand side equals the right-hand side, so check. 4 is a solution to that equation. Now it's worth pointing out that it's not the only solution, so there's another solution to this equation, x equals -1. And that's just to remind you that just because you find a solution to an equation doesn't mean you've found all of them. So now let's look at this for differential equations. We're going to have tx prime equals 3x plus 4t minus 9. So when I see the t and the x prime, I should think immediately to myself, this is a differential equation because there's a derivative, x is the dependent variable, and we can assume that since the other variable that's appearing is t, that the prime means differentiate with respect to t, the independent variable. And we can ask if the function x of t equals t cubed minus 2t plus 3 is a solution, and we're going to do the same thing, we're just going to plug in. So on the left-hand side, we're supposed to take t and multiply it by x prime. So we take t, and if this is our guess for x, then we have to differentiate that. We get 3t squared minus 2t. So left-hand side is t times 3t squared minus 2t, or expanding 3t cubed minus 2t. Then we have to do the same thing on the right-hand side. The right-hand side says 3x plus 4t minus 9. So that's 3 times this whole expression for x plus 4t minus 9. And if you expand and simplify, that's 3t cubed minus 2t. And then you look at those two things, left-hand side and right-hand side, and you say, aha, they're the same, so that is a solution to the differential equation. And it's worth pointing out that it's not the only one, and in fact, any function of the form ct cubed minus 2t plus 3, where c is any constant, is also a solution to that differential equation. So, how do we find solutions? We've talked here about how to check if a given function is a solution, but how do we find solutions? There's two basic different kinds of tools. One thing you can do is to look for an analytical solution. That means you're trying to find a formula, like we wrote down here. You know, this is an analytical solution. We have a formula for the unknown function. But we know from having studied functions in this course that you can also represent a function as a table of numbers. And so there's this other way to find solutions to differential equations, which is numerically, where you don't get out a formula for the function, but you instead just get out a list of numbers that corresponds to the unknown function that you're trying to find. And I want to show you very simply how to do that second thing. You'll learn in later screencasts how to find analytical solutions for some very simple ODEs, but in terms of finding solutions, for most it's a bit more challenging than what we'll cover in this class, and if you're interested in that topic, you should take a course in differential equations. That would be a great thing to do. So for now, numerically, let's take a peek at that. And here's the idea. We'll start with a single differential equation with the form dx dt equals something. And what you should imagine is that x represents your position, t represents time, and then you know that the meaning of dx dt is velocity. So what f is some rule for your velocity, where if you know your current position and what time it is currently, then you know what your velocity is. And what you do to solve the differential equation numerically is you figure out your velocity wherever you start, you take a little step forward in time to a new position using that velocity, and then you calculate your velocity again, and then you move again, and then you calculate your velocity again, and then you move again, and you keep doing this over and over. Now, this turns out to be equivalent to local linear approximation that you studied in the screencast from some units back on derivatives. In the context of differential equations, we call it this, and this word here is not pronounced Euler, which is what it looks like. It's actually pronounced Euler. He was a German mathematician. And so Euler's method is the simplest example of a numerical method for solving differential equations. Its accuracy depends on how big your steps are in time, and it won't always work. And I'm going to try to emphasize some of these things through a couple of examples. Right now, I know this probably sounds like quite a lot, but let's try to make it clear with an example. So let's take this differential equation, dx dt equals 10 minus 2x. And if we're going to actually solve this, and if we're imagining this as being our position as a function of time, we should say what our position is at the start of time. So we'll say that our position, when time equals 0, equals 1. Maybe that's, 1 mile east of St. Paul, Minnesota, or something, okay? And this is what's referred to as an initial condition, right? This is how things start out in your problem. This is the differential equation. This is the initial condition, okay? So I chose a differential equation on purpose that I happen to know the exact analytical solution to. I'm not going to give you the formula right now, but I've plotted it as this black curve down here, and the red dot represents where we're starting out. At time equals 0, the t kind of got cut off here, but this is at time equals 0, we're at a position of 1. All right, and so this is the exact solution, and we'll see how our approximate numerical solution matches up with it. So at time equals 0, I'm at a position of 1, and I can ask, at that point, what is my velocity? Well, the rule for velocity is 10 minus 2x. So for us, I have to take this value 1, I have to plug it in here, right? 10 minus 2x, that's 10 minus 2, that's 8. So our velocity is 8. It's like we're going east at 8 miles per hour. And I decide that I'm going to evolve forward in time a quarter of an hour. That's a totally arbitrary decision, but I'm going to jump now to time equals a quarter of an hour, and I'm going to ask, where am I now? Well, I'm at my old position, which was 1, plus I drove for an extra quarter of an hour at 8 miles per hour. So that tells me I should go an additional 1/4 of 8 is 2. I should go an additional 2 miles from where I started. So 1 plus 2 is 3. 3 is my new position. Okay. Now I'm going to ask, and I've plotted that point here, by the way. So this is at 0.25 comma 3. That's this blue dot here. Now we're going to repeat this. I'm going to ask, at this new position, what's my velocity? Well, my position is 3, so I've got to take that, plug it into the velocity rule here. 10 minus 2 times 3 is 4. Okay, so now I'm driving at 4 miles per hour. And I'm going to drive for an additional quarter of an hour. And if I do that, the time is now 0.5 hours, because we went for an additional quarter of an hour. And my new position is my old position, my previous one, which is 3, plus I drove an additional quarter of an hour at 4 miles per hour. I'm driving very slowly. That's an additional 1 mile. 3 plus 1 is 4. So my new position is 4. Same thing now. Take that new position, I plug it into the velocity rule. 10 minus 2 times 4 is 2. So now I'm going to be driving at 2 miles per hour. Okay? And so I evolve forward 0.25 units of time, 0.25 hours, and my new position is going to be my previous position of 4 plus a quarter of an hour times 2 miles per hour, and that puts me at 4.5. So I'm now 4.5 miles east of St. Paul, okay? And then I have to take 4.5, I have to plug it into my velocity rule. 10 minus 2 times 4.5, that's 10 minus 9, which is 1. So my new velocity is 1, and I can just continue this. And doing this results in this series of blue dots, and these 4 blue dots correspond to these last 4 entries in the table here, and then I'll just continue the process for you and show you some more dots that occur from continuing this. So you can see we're not exactly tracing out the black curve. The black curve's the exact solution. We're not exactly tracing it out, but we're doing a decent job. And this is called Euler's method. Now, students often rightly ask, how did you know to take jumps of a quarter of an hour? Sometimes I'll call that jump size delta t. And the answer is you don't know. It's just an experiment. In general, the bigger jumps you take, the worse a job you will do approximating the real solution. So smaller is always better in terms of how small you have to go. You don't know. You want to go small enough such that you're getting an accurate and a consistent answer. With that in mind, let me show you a second set of data. What if instead of using time equals 0.25, I had used a larger value, which means it should be less accurate? Well, if I do that, I get these green dots here, and you can see that those don't do a very good job at all of approximating the unknown function. So this is Euler's method, and let me just show you the same idea for a system of differential equations. So here, there are two unknown dependent variables. There's x and y, and we have a differential equation for each in terms of their derivatives, and the rule, the velocity rule for x and the velocity rule for y, depends on both x and y. And we'll talk about this more in the next screencast on modeling, but basically x and y kind of interact with each other here. So we're going to have x of t and y of t that we have to figure out. And we'll choose our initial conditions that at the start of time, x is 3 and y is 1. And I won't make graphs for you here, but I will make a table of numbers. And I apologize that the font is kind of small, but there are some computations to be done, so I got to leave space for it. So at time equals 0, x equals 3 and y equals 1. That's our initial condition, right? That's what we call this, the initial condition. And we can ask, what is the velocity for x and what's the velocity for y? So to find the velocity for x, I have to look at the right-hand side here and plug in the values of x and y. So I get 3, which is x, minus 3 times 1, which is x times y. Well, that's just 3 minus 3, which is 0. So dx dt, my x velocity, is going to be 0. Then for y, I have to do negative y plus 2xy. That's negative 1 plus 2 times 3 times 1. That gives me a velocity of 5. So now we can evolve forward in time a little bit. I'm going to evolve forward 0.01 time units. So my new value for x will be the old x position, which is 3, plus the additional amount of time I drove, which is 0.01, times my x velocity, which is 0, so I stay where I am. I stay at 3. For y, I'm going to be at my old position of 1, plus the amount of time we drove, 0.01, times the y velocity, which is 5, so that takes me to 1.05 is my new position for y. Now I have to calculate new velocities. So I got to calculate dx dt. I take 3 and I take 1.05, and I plug them both into this first equation. That tells me dx dt. It turns out to be minus 0.15. Then I take them both and I plug them into this second equation. That gives me dy dt, which turns out to be 5.25. Then I can go ahead and evolve my position again. So now time is going to be 0.02. My new x position will be 3 plus the extra amount of time we drove times our x velocity, which in this case happens to be negative. So my new x position is 2.9985. Same thing for y. It's my previous position, 1.05, plus the amount of time we drove times our velocity in y, which was 5.25. That puts me at 1.1025. Then I can take those new values of x and y, and I can plug them up here into the right-hand sides of these equations to get the new values of dx dt and dy dt, and so on. And that's how you apply Euler's method to a system of equations. Now, obviously, this is a very inefficient way to do this by hand or using your calculator. So computers are much better at doing this, and you will learn how to solve differential equations numerically using R, using the Project Mosaic software. But still, it's important to understand the basic idea of what's being done when you generate a numerical solution to a differential equation. That's the idea. So we've come to the end of the lesson. I want you to ask yourself if you can distinguish between algebraic and differential equations, if you can identify the independent and the dependent variables in an ordinary differential equation or a system of equations. You should be able to check if a candidate function is a solution to an ODE. And you should be able to approximate an ODE's solution or the solution to a system of ODEs using Euler's method. All right, thanks for listening.